This question belongs to operating system subject and was asked in GATE CSE 1990. It is match the following question. So the question states match the pairs. We have been given two lists, list 1 and list 2. List 1 contains critical region, wait slash signal, working set and deadlock. And list 2 contains Bohr monitor, mutual exclusion, principle of locality and circular wait. Let us see all the options one by one. So what is a critical section? So what is a critical section? So critical section is a part of code where we are having the shared resources. So it is part of code where a process is accessing shared resources. Shared resources. So let me give you an example for this. Let us assume we have two programs. Program P1 is, it has some code over here, then it has read on a variable A, then it has increment on the variable A, and then it has write on variable A. Program P2 starts with read on variable A, it then decrements the variable, and then it can write on variable A, and then it has some operations. So and A is a shared variable, it is present in the memory. Let us assume it has a value 10. So what happens over here? We can see that A is a shared variable, which means it is a shared resource, and in this part of code P1 is accessing A, and in this part of code P2 is accessing A. So this part of code is called critical section for P2, and this part of code is called critical section for P1. So what happens is that for due to this critical section, if both the programs are executing parallelly, then race condition will occur. What is a race condition? Race condition means we will get different output if we have different execution sequences. Me give you an example for this one. Let us assume we are executing P1 followed by P2. So what happens? First P1 reads A to be 10, then it increments A, which means makes it 11, then it writes A, which means it writes 11 over here. Then when P2 comes, P2 reads A to be 11, then it decrements it to be 10 and then writes over here 10. So we get the output to be 10. But let us suppose we are having a parallel execution. So what happens in parallel execution is, let me clear this stuff out. Yes. So in parallel execution, P1 reads A to be 10. Let us assume now P1 gets preempted and P2 comes in the scene. P2 reads A to be 10. Now P2 decrements 10 to 9 and P2 writes A, which means makes over here 9. Then P1 comes and it increments in its local memory 10 to 11. Then it writes A, which means it writes over here 11. What is the output of parallel execution? P1 parallel to P2, output is 11. So this is race conditioning. It means we are getting different outputs if we have different speed of execution or different sequence of execution. So we need to make sure that at a particular point of time only one program is in this critical section, which can be done, which means we need to ensure mutual exclusion. Thus critical section is related to mutual exclusion. Mutual exclusion means at a particular point of time, to ensure consistency, only one program should be able to access the critical section or access the variable. So critical section is mapped to this mutual exclusion, which means option Q. Now let us see the next option. What is the second option? The second option is wait slash signal. So what is wait slash signal? Wait and slash are basically commands which, when a process goes on wait state, then wait command is used, and when block state, then wait command is used, and when we want to bring the process back from block state to the working state, then we use the signal command. So first of all, let me tell you what is a monitor. As we have seen just now that we have critical section problem, and critical section problem can be solved by synchronization methods. Synchronization means we need to synchronize which process will enter the critical section. Now what is a monitor? Monitor is basically a high level synchronization construct. So why is it used? It is used to solve the critical section problem. And in monitor, it allowed only safe sharing of abstract data. Their abstract data was A. So it allows safe sharing of the abstract data type A among the concurrent processes P1 and P2. For that example, there can be many processes also P1, P2 up to Pn. Or we can also see that monitor is basically a class like a Java class. A monitor is like a class in which a class will have data as well as functions in which all the data is private. Private data means no one can access the data from outside the class, in which all the data is private and with the special restriction that only one method. It will have many methods. It has a restriction that only one method within any given monitor object will be active at a point of time. So only one method can be active at a point of time. Now, there is another type of monitor which is called horse monitor. Horse monitor. So what is a horse monitor is? So horse monitor is basically a monitor with a monitor with a blocking conditional variable. Blocking condition variables is called a horse monitor. And or it is also called hold time monitor, or we can say signal and weight monitors. Now let me show you the diagram for this. So this is basically a diagram for a monitor. So you can easily see that monitors can be have a weight and signal operations. So weight is used to move a process to the block state and signal is used to bring it back from the block state. So monitors can be mapped to this weight and signal, horse monitor. So B can be mapped to P. Now let us see the third option. So the third option is working set. So what is a working set? So let us suppose we are running a process. So when we are running a process, then a process is divided into page and main memory is divided into frames. So let us suppose we have a process over here, process P1. Process is divided into page and we have a main memory. Main memory is divided into frames. Now we need, as the process is larger and we may have many processes, we can have a process P22, we can have a process P32, we can have all the process up to Pn. So we need, and they are also divided into pages. So we need to make sure that all the process get sufficient amount of frames in the main memories. One page can occupy one frame, one page equals to one frame. So we need to make sure that all the processes get sufficient amount of main memory frames. And there are various techniques for this. Like initially we can keep all the frames empty and then when a request arrives, there will be page fault and then we can bring the page. But we have a working set algo too for this. Working set algo. So what a working set is, like suppose we are having a program P and we are having some code in it. Let us suppose a loop over here which access some variable. So during this entire execution of the loop, we know only few things will be accessed, like only some variables might be accessed, another variable A might be accessed, this loop variable might be accessed. So they will be present in the closed locality. It might be present that I is present over here, A is present over here. So during this entire loop, only these two pages will be needed. What is a working set? We can say that working set refers to the pages that are needed by a process at a particular point of time. So we need to bring this entire working set to the main memory so that if we will bring these two pages, then during the entire execution of the loop, there will be no page fault as we will have all the required data in the main memory. So what is a working set? Working set is the set of pages which are required at a particular point of time during the execution of a program. And working set algo makes sure that we bring the entire working set to the main memory so as to reduce the page faults. Thus, and you know, working set is based on locality of reference, as the programs that are being as the pages that are being run at a particular point of time, in the at that point of time only, the pages which are close to that the current page will only be referred. This is called the locality of reference. So working set is based on locality of reference. So C is related to R. Now let us see the fourth option. The fourth option is deadlock. So what is a deadlock? A deadlock is a condition in which more than one processes are there in the scene and they are not able to execute because each one is waiting for a resource that is held by another process. Let me give you an example. Let us suppose we have three processes P1, P2 and P3, and we have a resource A with one instance. It is given to process P1, and we have a resource B with one instance which is given to P2. We have a resource C with one instance which is given to P3, and P1 is requesting for B, P2 is requesting for C, and P3 is requesting for A. Here we have multiple processes and they are in block state or waiting state because they are asking for a resource which is being held by another process which is also in the block state. So this is called deadlock. And what are the necessary conditions for deadlock? Necessary conditions for deadlock are mutual exclusion. Mutual exclusion means at a particular point of time, a resource should be held by only one process. Another one is hold and wait. Hold and wait means a process should hold the resource and should wait till it doesn't get its required resources. Third one is circular wait. Circular wait means the process should wait for the resources in circular manner. As here P1 is dependent on P2, P2 is dependent on P3 and P3 is dependent on P1. And fourth one is mutual exclusion, hold and wait, circular wait, and no preemption. No preemption means none of the process should be given the high priority and should be able to preempt another process. So it might not be the case that P3 is having higher priority, so it will be able to preempt P2. We shouldn't allow this. So deadlock has these four necessary conditions. So deadlock is also related to circular wait. So D option can be mapped to S. So the correct mapping is critical map region has been mapped to mutual exclusion, wait and signal has been mapped to horse monitor, working set is mapped to principle of locality, and deadlock is mapped to circular wait. This question belongs to database management system and was asked in GATE CSE 1990. So the question states, match the pairs in the following questions. Secondary index, non-procedural query language, closure of a set of attributes, and non-natural join. So what is an index? Suppose we have a database file. We can have many attributes, like we can have serial number, we can have roll number, we can have name. If we have student data, then we can have these fields. Now we will create an index so that we can search effectively and faster any file. Then indexing can be of various types. We can have primary indexing. Primary indexing means we are searching on a candidate key. Like if assume candidate key is a roll number. So we are searching on the candidate key, roll number, and roll number is sorted. Candidate key plus it is sorted. And what is a secondary indexing? We can also have a secondary indexing. Secondary indexing means we are searching on a candidate key or a non-candidate key, but it is non-sorted. Like name, I like we can assume name. Yeah, let us assume name and phone number. So phone number, either we can have it sorted by the sorted, like we can have starting with 6, starting with 7, starting with 8. So we can have secondary indexing over phone number, which is non-sorted candidate key, or we can have on non-sorted non-candidate key, like name. Name is non-sorted and is non-candidate key. So secondary index is on non-sorted things and it can be on candidate key or non-candidate key. And we can, for secondary indexing, we can use B tree or B plus tree. We can use them for these indexings. So secondary index is related to B tree. So option Q is true. Let us see the next option. So next option is non-procedural query language. So what are the types of query language? First, let me tell you this. A query language can be a procedural query language or a non-procedural query language. So procedural query language tells us what data we need to bring and how to bring it. And non-procedural query language just tells what data we need to bring but doesn't tell how we need to bring it. Relational algebra is an example of procedural query language. A non-procedural query language can be of two types. It can be either with tuple relational calculus or it can be domain relational calculus. Example of tuple relational calculus is SQL language, and example of domain relational calculus is query by example. It is a GUI based method. So we can easily see that non-procedural query language can be either be tuple relational calculus or domain relational calculus. Thus, non-procedural query language can be mapped to domain calculus, which is option R. Now, let us see the next option. So, next option states closure on a set of attributes. Okay, let us suppose we have some functional dependencies like A derives BC and B derives D. Now, assume we want to find A closure. A closure means what all we can derive from A. So from A we can derive A. Using this FD we can derive B and C from A, and we can from B you can derive D from A. Thus A closure equals to ABCD. Thus closure on set of attributes works on the functional dependencies. Thus option P is true. Now let us see the last option. Last option says natural join. Yes. What is a natural join? Suppose we have a table with fields A, B and C and values like 1, 2, 3, 1, 2, 5, 2, 4, 6. This is table T1. We have another table T2 with attributes. Let us assume A, B, D with values 1, 2, 8, 2, 3, 5 and 196. So what is a natural join is? Natural join means joining the two tables, but with a condition that if we are joining, one is normal cross product, it is a natural normal join, but a natural join means we will do the cross product with the condition that the common attributes, what is the common attributes of T1 and T2? AB. AB should be common in all the fields that come in T1 cross T1 natural join T2. So we will have AB, C as well as T. We have common fields are 1 2. Is 1 2 present over here? Yes. So it will have an entry for 1 2. We will have 1 2. What is value of C3? What is value of D? 8. Now do we have another 1 2 over here? No. Do we have for this 1 2? 1 2. Do we have 1 2 over here? Yes. So 1 2 5 8 5 8 2 4. Do we have 2 4 over here? No. So the answer is this. So this natural join is basically a type of relational algebra operations. So answer is QRPS. This question belongs to compiler design subject and was asked in GATE CSC 1990. So the question states match the pairs in the following questions. We have been given two lists, list 1 and list 2. List 1 contains pointer data type, activation record, repeat until and coercion. List 2 contains type conversion, dynamic data structure, recursion and non-deterministic loop. Let us see all of them one by one. So option A is pointer data type. So what is a pointer? Pointer is nothing, just it's a variable which is used to store an address. It will have its own address and it will store another address, and at that address we will have some data. Let us suppose 10 data is there. So this variable A is called a pointer variable which is used to store address of this variable B. So where is pointer data type used? Pointer data type is used in dynamic data structures. What are dynamic data structures? We can have static data structure or dynamic data structures. Static like array. Once we have created an array, we can't remove the number of blocks in array, and even we can't add the number of blocks. What is a dynamic data structure? Assume a stack. A stack implemented using list. We can add more items, we can remove the items. A linked list, it's a best example for dynamic data structure. We can add the nodes, we can define the structure, and then we can add the nodes by using this new operation command. So this is a dynamic data structure. We can also remove the nodes. A tree, we can add the nodes and we can also remove the nodes. And how are these links? A dynamic data structure is linked using a pointer. This is a pointer pointing to the address of this. This is a pointer pointing to address of this. And in the tree, this is a pointer pointing to address of this. Thus, pointer is related to dynamic data structure. Option Q. Let us see the second option. The second option is activation record. So what is an activation record? So an activation record is activation record. When we are executing a program, let us suppose we have a program P1. This has some main statement, main function, which calls function F1, then calls function F2, and then it ends. So we have a stack. This stack is present in the main memory. So whenever main is called, we will push main in this stack. Main will come over here. Then when F1 is called, F1 comes over here. When F2 is called, F2 comes over here. What is coming over here? The thing that is coming over here is activation record. An activation record of F1 is pushed. An activation record of F2 is pushed. An activation record of main is pushed. And what are the contents of activation record? These are the contents of activation record. So an activation record contains return value. What will this function F2 return? What will this function F1 return? Actual parameters, the parameters that are passed to this function. Control link and access link are used when we are having the scope problem. Saved machine status, the status of machine before calling and after calling the function. The local data of a function and the temporary variables stored. So these activation record is basically pushed in this function call stack for each function. This activation record is linked to recursion, because what is recursion? During recursion, what we are doing? During recursion also we are using a stack. And if we are having a recursive call, let us suppose F1 on X, and inside this we are calling F1 on X minus minus. Then what happens? First F1 will be pushed with X, and activation record of F1 with X will be pushed. Then F1 activation record, let us suppose X was 5. Then F1 with 5 will be pushed, then F1 with 4, F1 with 3, F1 with 2. So during recursion we are pushing the activation record of the same function. So activation record is related to recursion. Let us see the next option. So the next option is repeat until. So what is the meaning of repeat until is? Suppose we are having a loop. So whenever we are having a loop, we need to give the condition like when this loop will stop. Or when we are having a do while loop, let us suppose we have a do while loop, do while. So it will do something while this condition is true. And if we write a condition which will never happen, then we will have a non-deterministic loop. Thus, repeat until is related to non-deterministic loop. Now let us see the last option. The last option states coercion. So what is coercion? Coercion is related to type conversion. I will tell you how. So suppose we are in C program, we are writing int a equals to 10. Is it correct? Yes. Is it correct? It is correct. Now if we are writing a equals to 10.5, and then let us suppose b equals to 10.5, and then we are printing b. What will it print? It will print 10. What happens? It is a float, and it is accepting int. So float will be converted to int internally by the program, and it is called coercion. It is called implicit conversion. The conversion that is done by the compiler itself is called implicit conversion or coercion. Now if we write int c equals to round, it will give you an error, as it is not an implicit conversion. And there are some conversions that we can do by specifying something like int a equals to, we want to convert to int the value 15.5. If we write this int over here to match with this int, then it is called explicit conversion or casting. But coercion is related to implicit conversion and is done by compiler. Thus coercion is related to type conversion or implicit type conversion. So the option matching is QRSP. This question belongs to programming subject and was asked in GATE CSE 1990. So the question states, match the pairs in the following questions. Smalltalk, Lisp, Prolog and Val. These are all programming languages. And the second list contains logical programming, data flow programming, functional programming and object-oriented programming. So these are programming paradigms. So what is a programming paradigm? Suppose we are doing a programming. So why is programming done? Programming is done to solve a problem. And if we want to solve a problem, then there can be various approaches to solve the problem. And these approaches are called paradigms of programming. Let me tell you all the approaches. So what is a logical programming approach? Logic programming approach. So what logic programming approach does is that it's based on a knowledge base. So we have a knowledge base, like how to solve the problem, and we have a problem. So the input will be a knowledge base will be given and a problem will be given, and we have to find out how to solve the problem. So it's different from other programming language as it is based on this knowledge based. So the programming language that is logical programming language is Prolog. So Prolog is basically a logical programming language. The second one is data flow programming language. We can also call it database programming language. So what do you mean by data flow? So here, instead of writing the steps to solve the problem will be basically dependent on data and its flow. Like in database. In database, what we are doing? We will have a create table command, create table T1. It will have various fields like student name, ID, roll number. So this is all data and it's stored in tabular format. And we can have operations like add, remove, update. So this data is flowing through these operations. So the programming which is based on data is called data flow programming. And the example of this programming is Lisp. So Lisp is basically, wait, this is related to S, R, P and Q. So data flow programming, VAL. VAL is a data flow programming language. Then we have the third optional, which is functional programming language. So what is a functional programming language? We all of us know the mathematics functions. So what a mathematic function do? It basically has a sequence of steps to do a particular task. And what is a programming functional paradigms? Here all the tasks need to be done as a function which basically does some specific tasks. And the last one is object oriented programming language. So object oriented programming language, its example is, we can say Python is an object oriented programming language, Java is a Python object oriented programming language, C++ is an object oriented programming language, as well as Smalltalk. Smalltalk is a pure object oriented programming language. It's pure object oriented. So what does object oriented means? Object oriented means we will have objects as well as class, and whenever we want to create a data structure we will instantiate these objects based on the class. So what are objects and class? Let us take the example of our laptop. So we will have a laptop class. What will it contain? It will contain some data and function. What will its data? Its data will be how many keyboards are there, how many mouse are there, which type of keyboard is there, how many screens are there, which type of screen is there, and what will be its function? Its function will be opening up, shutting down, writing something, displaying something. Now this is a class. Now there can be various brands like Dell, Lenovo, and they can also have different versions. Like we can have IdeaPad, we can have a gaming version. Now all these will have these basic functions as well as data. So these are objects and we create the objects based on these class. So it's called object oriented programming. So, and the object oriented programming language is Smalltalk. It's a pure object oriented programming language. So the correct mapping is SRPQ. This question belongs to algorithm subject and was asked in GATE 1990. So the question states, match the pairs in the following questions. So we have been given some algorithm in the list one and we need to match whether there are greedy, dynamic programming, divide and conquer or depth first search. So the algos are Strassen's matrix multiplication algorithm, Kruskal minimum spanning tree algorithm, bi-connected components algorithm and Floyd shortest path algorithm. So let me first explain you what is Kruskal minimum spanning tree algorithm. So first, what is a spanning tree? A spanning tree is basically a subgraph of a graph which has all vertices of the graph. It has all vertices. Number of edges in spanning tree equals to number of vertices in spanning tree minus 1, and it is a tree, which means it is acyclic and connected. So let me draw a spanning tree so that you can get it more clearly. So suppose this is a graph. So what is a spanning tree for this? Spanning tree, it will have all the vertices. It will have number of edges equals to number of vertices minus 1, which means 3 edges, and it should be acyclic. So like this it will happen. We can have various spanning trees. Now what is the minimum cost spanning tree? If we have cost associated with these vertex edges, then what is the minimum cost that we can get for a spanning tree? Like for this one, cost would be 10, 20, 30. So total cost is 30 plus 2, 50 plus 10, 60. Total cost is 60. And if we have another spanning tree like this, we can have various spanning tree for this, but for this the cost will be 40 plus 10, 50 plus 2, 20, 70, 70. So if we have various spanning tree, what is the minimum cost? So this can be done using Kruskal algorithm. So what Kruskal does is, it is based on greedy method. So what greedy method states? We will look at the choice which is best suitable at a present point of time. So we make it greedy by assuming that we will always take the minimum cost. We'll always take the minimum cost, first 10, then 20, and then 30, and by doing so we will also avoid the cycles. If a minimum cost is making a cycle, we will not take it and take the next minimum. So this is the Kruskal algorithm. So Kruskal is related to greedy method, option B. Now let us see the next option. So the next option says bi-connected component. So what is a bi-connected component? Suppose we have a graph given. So a bi-connected, option C, bi-connected component. So if we have a graph G, then a bi-connected component is a maximal bi-connected graph. All maximal bi-connected graph is called the bi-connected components. And what is a bi-connected graph? A bi-connected graph means that a graph is called a bi-connected graph if among all the vertices there exist two vertex disjoint paths, means no vertex should be common in that path. And this bi-connected components can be easily done by DSSS algorithm, as we just need to make a scan and make sure that no vertices are repeating, and in that case we will get a bi-connected component and a bi-connected graph. Now the option D is Floyd shortest path algorithm. So Floyd is basically all pair shortest path algorithm. Let us suppose we have a graph like this, and it may be connected like this. It will have various costs like C1, C2, C3, C4, C5, C6. So we need to find out if we start from this vertex V1. So what is the minimum cost in which we can reach to V2? We can go by C1 or by C6, C5, C3, or by C6, C5, C4, C2. So what is the minimum cost to reach? And we need to find it for all the pairs, like for V1, V2, V3, V4, V5. What is the minimum cost to reach V1, V2, V3, V4, V5? So it's basically done using dynamic programming. I will give you the link which you can refer for the code for dynamic programming for this Floyd-Warshall algorithm. So Floyd-Warshall is based on dynamic programming. So this is the link. You can refer to this link and you will get to know how it is related to dynamic programming. It is a Geek for Geek link which tells Floyd-Warshall algorithm DP solution. Now let us see the next option A. So what is option A? Option A is Strassen's matrix multiplication. Suppose we have two matrices M1 and M2 of size M cross N and M2 of size N cross P, and we need to multiply them. So what is the complexity? So if we do by 3 loops, then the complexity will come out to be order of n cube. But we have a better solution. Suppose we divide A into 4 parts, A, B, C and D of size n by 2 and n by 2. This is n by 2 and this is n by 2. So all A, B, C, D have sizes n by 2 and n by 2. And E, F, G, H also have sizes n by 2 cross n by 2. Now we have these 7 predefined formulas. We need to remember them. Here each A, B, C, D, E, F, G, H is an n by 2 cross n by 2 matrix. And if we do perform these operations, then we will get the resultant matrix which is of size n cross n for the multiplication. So let us count the number of multiplication and addition. Here let us count the additions. So 1, 2, subtraction can also be counted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have 18 additions. Let us count the number of multiplications. 1, 2, 3, 4, 5, 6, 7. We have 7 multiplications. So what will be the complexity? And the size of each of the matrix which is being multiplied is n by 2 cross n by 2. And size of each of the matrix being added is n by 2 cross n by 2. So the complexity is 7 additions 70 n by 2 plus 18, 7 multiplications and 18 addition. 18 addition of n by 2 matrices of the size 18 n by 2 square. So the complexity will come out to be by Master's theorem order of n to the power 2.81. We can easily see it is based on divide and conquer approach. We are just dividing the matrices into smaller part. N cross n is divided into n by 2 cross n by 2 and then the smaller problem is being solved. Thus, Strasson's matrix multiplication is based on divide and conquer, which is R. So the correct mapping is RBSQ. This question belongs to data structure subject and was asked in GATE 1990. So the question states, match the pairs in the following questions. So we have been given two lists, list 1 and list 2, and we need to do match the pairs. So list 1 contains options like a heap construction, constructing hash table with linear probing, avial tree construction, and digital tree construction. And list 2 contains the complexities, order of n log n, order of n square, and order of n log n. So let us see all of them one by one. So heap construction. So what is a heap? Heap is an almost complete binary tree. So let us suppose we have almost complete binary tree and we are constructing it. So at a given point, what will be the complexity of adding a new node? Adding a new node needs to do the heapify operation, and heapify equals to height of tree. Height of this complete binary tree is log n. So one heapify will take log n, and n heapify will take n log n. So complexity can be n log n. But we have another method to do heapify. A heap construction can be done by the build heap method. So what a build heap method says is that, I will tell you the build heap method. Suppose we have a heap like this, 25, 200. We will first initially make the tree, which can be done in constant time, as we will keep it in the array itself. So let us suppose we have the nodes like this, 80, 90, over here 100, then 53, 99, 17, 13. Okay, let us assume we are making a max heap. So max heap means maximum item should be at the top. Let us do the indexing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we start from the index n by 2 lower bound. So what is n by 2 lower bound? 11 by 2 lower bound? It's 5. So we start from 5. We start from 5th index and check whether it is a max heap or not down it works. So how many comparisons it need to make at max? One element needs to make one comparison at a max. Comparison or swap at a max. So 80 checks 17 and 13, it is a max heap. Then we check to the next item. We check from n by 2 lower bound to 1. We will do heapify. But down heapify. We will check down. Now 400 will check 53 and 99. These are perfect. Now 300 will check 900. Let us assume it to be 1000. 300 will check 90 and 1000. It is not a max heap. So 1000 will come up and 300 will come down. Now 200 will ask 480. 400 will come up, 200 will come down. Now 25 will ask 400 and 1000. So 1000 will come up and 25 will come down. Now again, see here, 300 will come up and 25 will come down. So at this level, how many nodes are there at the last level in an almost complete binary tree? N by 2 nodes are there, and these n by 2 nodes won't have any comparison or swap. N by 2 has 0 swap, and at previous level we will have n by 2 whole square, and these will have one swap at a max to the height of the tree down towards. Then above at level will have n by 2 cube, and they will have 2 swap at max, and same at the root we will have n by 2 to the power log n levels, and they can have log n swaps at a max, log n minus 1. Thus, if we will solve this, then we will get a decreasing GP, and if we calculate it, we will get the complexity to be order of n. You just need to add these terms like n by 2 into 0 plus n by 2 square into 1 plus n by 2 cube into 2 plus n by 2 cube into 3, 2 4 into 3 up till n by 2 power log n into log n minus 1. You will get a decreasing GP and the complexity will come out to be order of n. So another method to do it can be done in order of n. So is there an option matching order of n? Yes, there is an option matching order of n. So we will take the most efficient one. So the answer for option A would be order of n. A heap tree construction can be done in order of n. So the answer is A will be mapped to Q. Let us see option B. Option B says constructing a hash table with linear probing. So what is a linear probing? Suppose we have a hash table with the fields 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Now suppose a key comes, we are using key mod 10 as our hash function. Now suppose 5 comes, then 5 mod 10 is 5, it will come to 5. Then 15 comes, 15 mod 10 is 5, but it is not, it is already filled, so it will check the next slot till it will get an empty slot. 15 will come over here, 18 will come over here, then if we have 17 will come over here, then if we have 35 it will come over here, filled, so 35 will come over here. Now assuming that every time we are getting the unit term as 5, like we will have 5, 15, 25, 35, 45, 55. So what will be the complexity? So the complexity would be, assume every time we are getting 5. So 5 will come over here. What will be the number of probe? 0 probe. 5 will come over here. 15, 15 will check over here, filled, so it will come over here. Number of probes? 1. 25 will do 2 probes and come over here. 35 will do 3 probes and come over here. And what can be the maximum number of probes? It can be n minus 1. So what can be the complexity? Complexity will be sum of all the probes. 0 plus 1 plus 2 plus 3 up to n minus 1. So this series will sum out to be n minus 1 into n by 2, which is equals to order of n square. So constructing a hash table can be done at a worst case complexity of order of n square. So option R is matching. Now let us see option 3. So option 3 is saying AVL tree construction. So what is an AVL tree? AVL tree is basically a height balanced tree. So AVL tree is basically a height balanced tree. And what, so we need to basically balance the height, and balancing the height means left one should not go much. We cannot have skewed trees like this, like we cannot have a skewed tree like this, and it is done using balance factor. So this is skewed, and balance factor equals to left height minus right height, and balance factor should be between 1 and 0, between 1 and minus 1. It should be between these, but we need to just remember this: the height of balanced trees are approx log n. So if we are doing some additions, like an addition over here, then 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 for each addition we need to do the checking up to the above height. So for n additions we need to check for n log n times. You can assume it to be like this. So the complexity comes out to be n log n. Or we can also assume in an AVL tree, when we do the in order, its in order is sorted. Avial tree in order is sorted order. So now how can we make it using another method? Let us assume we are given an array. So we will first sort it. What will be its complexity? Order of n log n. And then creating a tree from an array directly will take constant time only. So the overall complexity will be order of n log n. So avial tree construction can be done by two methods and both will give complexity n log n. So this can be mapped to anyone P or S. Now the fourth option says digital trie construction. So what is a digital trie? Suppose we are creating n keys in a digital trie and each having m size. So the complexity for digital trie construction is order of n into m. Order of n into m is the complexity. But here we can see m is not there in the options. Then we can assume m to be constant order of n. But we can see order of n is already taken. Then we can also assume that in a digital trie also behaves like a BST. And height of BST is order of log n. Thus it will have an average key size value will be order of log n. M will be equal to log n as it behaves like a BST. So the complexity would be T of n equals to order of n into m, and m is approximately equal to log n. So the answer is order of n log n. So it will map to P or S. So the correct mapping is QR, and both P and S are same, so anyone can be mapped to anyone. But here, see, this is the maximum bound for avial tree construction, and this is big O and this is omega. Big O means the complexity will be less than this, and the avial tree we assumed complexity will be less than this, and in digital trie it will have minimum this. So digital trie will have omega, so digital trie will map to P and avial tree will map to S. So we will have a mapping QRSP. This question belongs to compiler design subject and was asked in GATE CSE 1990. So the question states, match the pairs in the following question. List 1 contains lexical analysis, code optimization, code generation and abelian group, and list 2 has DAGs, directed acyclic graph, syntax trees, pushdown automata and finite automata. So these three belongs to the phases of compiler. Let me tell you all the phases. So what happens is that when we write a high level language, suppose we have written a file example1.c, it's a high level language. When we give it to compiler, then compiler will convert it into assembly level language. And these are the phases of compiler: lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, code optimizer and target code generation. Let us see this lexical analysis phase. So lexical analysis phase, what it does is that it checks, it matches the lexemes, with patterns to generate tokens. So what it does is that suppose we have a C program and it has a statement int a equals to 5. So lexical analyzer will scan from left to right. It match these lexemes. Int is a lexeme, a is a lexeme, equal to is a lexeme, 5 is a lexeme, semicolon is a lexeme. So it match lexeme with patterns. And how it does this pattern matching? It does this pattern matching using finite automata with outputs. So these have the patterns. It matches the lexemes with patterns using finite automata to generate the tokens. And what are tokens? Tokens are int is a token, a is a token, equal to is a token, 5 is a token, and semicolon is a token. So in the lexical analysis phase, finite automata is used to produce tokens or strings in the form of identifiers. These are identifier a and 5 and keywords like int, constants from the program that will be stored in the symbol table. And the lexical analysis plays a major role in the pattern recognition. And this is done using finite automata. So lexical analyzer is mapped to finite automata. Now let us see code optimization. So what happens in this code optimization phase? In the syntax analysis phase, after generating the grammar in the form of syntax tree or derivation tree from the given token string. And then after the semantic analyzer, for checking the semantic correctness of the program, it will create a modified parse tree. Here we will get a modified parse tree. And the modified parse tree will be given to intermediate code generator, which will generate the intermediate code. Here intermediate code will be generated, like 3 address code will be generated. And what happens in this code optimizer is that we need to optimize the code for CPU as well as memory. And this can be done using a representation called directed acyclic graph is used to optimize the code, and it gives a tree like view to identify the common strings and eliminate them using, thus saving up memory and making it faster. Just remember, DAG is used to just do the code optimization phase. So DAG is mapped to P. Now we have code generation phase. So the semantic analyzer, which will give us the modified parse tree. So let me erase this stuff. So this semantic analysis phase will give us the modified, it will give us the token string, it will give us the parse tree, it will give us the modified parse tree, it will give us the intermediate code, and it will give us the optimized code. And this will give us assembly level language. So the semantic analyzer will give us the modified parse tree by using the grammar. And we can generate the intermediate code in the intermediate code generator. As it is based on the parse tree or modified parse tree or syntax tree, thus code generation is basically done on the syntax tree. So code generation is basically mapped to Q. Now let us see the other options. Abelian group. So what is an abelian group? So we know a group is a structure that satisfies the properties like closure, associativity, existence of identity, existence of inverse, but it do not have commutative property. But an abelian group is a group that is having the commutative property. Commutative property, what is a commutative property? Commutative property means if A is performing an operation with B, then it is equivalent to B performing the same operation with A. This is the commutative property. Now let me give you an example. Let us suppose we are having a group which is following the commutative property, and we need to check whether x to the power m, y to the power n, x to the power minus I, and y to the power minus k, whether it is equal to the identity or not. So first we will use the commutative property and convert it to x to the power m, x to the power minus I, y to the power n, y to the power minus k. Now we just need to check whether m equals to minus I and n equals to minus k, or we can say m equals to I or n equals to k. And this can easily be done, the comparisons can easily be done by using push down automata. Thus abelian group is mapped to push down automata, option R. Thus the correct mapping is S, P, Q and R. This question belongs to engineering mathematics and was asked in GATE 1990. So the question states, match the pair in the following questions. Here we are giving the mathematical structures like group, semigroup, monoid and abelian group, and we need to tell which property do they follow: associativity, identity, commutative and gene, left inverse. Let us suppose we have a group G on the operation this. Then we can make a table like this. It's good if you remember this table. First of all, we will have a semigroup, then we will have a monoid, then we will have a group, then we will have an abelian group, and we will have the properties like associativity, we will have identity, we will have left inverse, we will have commutativity. So just remember that semigroup follows associativity property, only this, not any of the others. A monoid is a semigroup with associativity as well as identity property. A group follows associativity, identity as well as left inverse but not commutativity. Abelian group follows all. Now let me tell you about the properties. What is associative property? It says A the operation and then C is it operation C. It should be equal to, it do not matter whether we perform first the operation with B and C or with A. Associative property says this. What is identity property? It says that there must exist an element E such that when A is being operated on the element, we will get the same element. So what is the identity for multiplication? Let us suppose we have 5 into 1, 5. So when 5 is operated on 1, we will get the same 5. So 1 is identity for multiplication. What is left inverse? Left inverse says that when we perform the operation A on B, then we should get E. So what is B? B equals to A inverse. So what's the example for this? Let us say the identity for 5 with addition. And the identity for addition is 0, as 5 plus 0 is always 5. So 0 is identity for addition, and we need to find the inverse of 5. So 5 when added with x should give 0. So x equals to minus 5. So inverse of 5 is minus 5. What is commutative property? It says that A applied with the operation should be equal to B applied with the operation. So multiplication is commutative. 5 into 3 is equal to 3 into 5. Addition is also commutative. 5 plus 3 equals to 3 plus 5. Thus, we need to make sure that these identities, you should remember this table and you should know the meaning of identity. Now let us see group. So the group follows associativity, identity and left inverse. So it can be mapped to left inverse. As abelian group and group both follows left inverse, but abelian group follows commutative property and no other follows commutative property. So it will get mapped to R. And group. Left inverse is done. Left inverse and commutative are the different things with group. Commutative is done, so left inverse will come over here. And semi-group will be mapped with associativity and monoid will be mapped with identity, as monoid only follows identity and not semi-group. The correct mapping will be S, P, Q and R. This question belongs to Digital Logic Design System and was asked in GATE 1990, and the topic name is Circuit Outputs. So the question states, choose the correct alternatives, more than one may be correct. Two NAND gates having open collector outputs are tied together as shown in the below figure. So in this figure, two NAND gates outputs are tied together using an open collector. Then the logic function y is implemented by the circuit is y equals to abc plus de, y equals to abc plus de whole complement, y equals to abc into de, y equals to abc into de whole complement, and y both c and d. So let us see the meaning of this. Two NAND gates having open collector outputs are tied together. So there may be two cases. Whenever we are tying the outputs of open collector together, whenever open collector is tied together, then two cases can occur. Then the common line can behave like either a wired AND gate or it can behave like a wired OR gate. So which means either this gate will behave like a wired AND gate or it will behave like a wired OR gate. Now we have some other logic for the wired AND gate. So if the gates being used are NAND gates, which means if we are using here NAND gates, if NAND gates are being used and the outputs are tied together, then it will create a wired AND configuration. And if the NOR gates are being used over here instead of NAND gates and the outputs are tied together, then it will behave like a wired OR. The reason for the first one behaving like a wired AND gate is because the output of NAND gate is low. The output of NAND gate is low whenever all the inputs are high. And this overall circuit will output a low signal whenever all the AND gates will output low signal. Because what is the truth table for NAND? Let us see for two inputs. So A and A and B whole complement NAND. So 00011011. For 00 it's 001, it's 0 complement, which means it's 1 into b whole complement. It's 1, it's 1, it's 1, and it's 0. So we can easily see that the output of NAND gate is low whenever all the inputs are high. So when all the inputs are high, the output will be low. And this output will be low when all the inputs will be high. And this output, as it is behaving like a wired AND, it will be low if all these will give a low signal, then this output will be low. Thus, NAND gate behaves like wired AND if we are using NAND gate. And if we are using a NOR gate, then it will behave like a wired OR. Why? Let me give you the first the truth table for the wired OR. So the wired OR truth tables look like this. Here 0, 0, it's 1, it's 0, it's 0, it's 0. So it will, because the output of NOR gate is low if either of its inputs are high. If either of the input is high, then the output will be low. As so the overall circuit will output a low signal if both the NOR gate outputs are low. So which means in this circuit we are having a wired AND over here. So here this can be replaced by an AND gate. Using an AND gate can be used to replace this one. Let me try it more precisely. So here we can have the configuration like this. So here we will get an AND gate. So let us see what will be the output. So here we are using a NAND gate, which means we will get A into B into C whole complement, and then we are doing AND with this one, D into E whole complement. So now, how will we evaluate it further? We will apply the De Morgan's law. So A into B whole complement. It can be written as Y equals to A into B into C. What is De Morgan's law? It says A into B whole complement is equals to A complement plus B complement, and A plus B whole complement equals to A complement into B complement. So using this law, A complement into B complement can be written as A plus B whole complement, which means ABC plus DE whole complement. So the answer is option B. This question belongs to database management system subject and was asked in GATE 1990. So the question states, choose the correct alternatives. Indicate which of the following statements are true. A relational database which is in 3NF may still have undesirable data redundancy because there may exist transitive functional dependencies, non-trivial functional dependencies involving prime attribute on the right side, non-trivial functional dependencies involving prime attributes only on the left side, non-trivial functional dependencies involving only prime attributes, and option E, both A, B, and D. So let's see. So basically there is a misconception regarding this transitive functional dependency. So I will try to remove this misconception. So let us see. Suppose there are two questions. Can 3NF have transitive functional dependency? This is a question. So let me give you answer. Yes, it can have a transitive functional dependency. I will prove it. So what is a transitive functional dependency? Let us suppose we have a relation and we have something like alpha determines beta and beta determines A, such that A doesn't belong to beta, as well as A doesn't belong to alpha. A doesn't belong to alpha. In this case, and if B can't determine alpha, then this is called alpha belongs to A is called a transitive functional dependency. Okay, now let me give you an example like whether we can have a transitive functional dependency in 3NF or not. So let's take this example. Suppose we have functional dependencies defined on the relation R, A, B, C, D such that the functional dependencies are AB determines CD, and we have CD determines AB, and we have A determines C. So what is the candidate key? Candidate key is AB, as we can have AB closure equals to, it determines AB as well as CD. So AB closure determines everything. Thus candidate key is AB, and we can have another candidate key as CD. And what are prime attributes? Everything is a prime attribute, A, B, C, and D. And what is a non-prime attribute? Nothing is a non-prime attribute. Everything is prime. So here we can easily see as everything that is being determined is a prime attribute, and we have no non-prime attribute. Thus this relation is in 3NF. So this relation is in 3NF. Now let us see whether it has transitive functional dependency or not. So see this. We can have something like, we have AB determines A. Yes, AB determines A, and it is it is trivial functional dependency. Can we have A determines C? Yes, we can have A determines C from this. Does, now using this, does C belongs to A? No, C doesn't belongs to A. Now whether C belongs to AB? No, C doesn't belongs to AB. And whether A determines AB? Yes, A determines AB. It's, no, A can't determine AB, because A just can determine only A as well as C. What is A closure? A closure is A and A closure is C. And can we determine anything with AC? No. So A can't determine AB because A can't determine B. Thus, this is a transitive functional dependency. Thus, it is a transitive functional dependency and it is 3NF. So, which means 3NF can have a transitive functional dependency. So, 3NF can have a transitive functional dependency. So, this is true. Now, let us see the next option. Now, we will see whether, let us see the next option. Just remember few of the basic things that I am writing over here. Can 3NF has a transitive functional dependency? Yes, 3NF can have a transitive functional dependency. And if there is a transitive functional dependency in 3NF, then we can have, let me write over here, we can have a transitive functional dependency with prime attribute on, let me rewrite this. We can have a transitive functional dependency such that prime attribute can be transitively dependent on candidate key. And this we seen in the previous example that I have given. In the example what we had a relation on ABCD, we had a relation on ABCD such that AB determines CD, CD determines AB, and A determines C, and we have seen that there we have seen that what we have seen that AB determines C was a transitive functional dependency. We have proved it, and that relation was in 3NF. So here we can easily see that we can have a prime attribute. C is a prime attribute, can be transitively dependent on candidate key. AB was candidate key. So we can have a prime attribute transitively dependent on candidate key. Now let me write the next point. We can't have a transitive functional dependency with candidate key determining a non-prime attribute. Okay, this is a very important thing. And let me tell you one more thing. In 3NF, everything is allowed except this non-super key determining a non-prime attribute. Okay, so let me tell you these things again. Let me tell you about, yeah, so let me tell you these things again. Okay, so we have seen that 3NF can have transitive functional dependency. I gave you an example for that, and from that example we can easily see that non-trivial functional dependency, there AB was determining C. So we can have non-trivial functional dependencies involving prime attribute on the right hand side. It had C on the right hand side, so this is allowed. So option B is also true. Now let us see non-trivial functional dependencies involving prime attribute only on the left side. So what is the meaning of prime attribute only on left side? Which means on right side we will have non-prime attribute, as it is a non-trivial functional dependency. If left is only left is prime, then the right will be non-prime. Whether this is allowed or not. So let us see. No, this is not allowed, as we cannot have non-prime attribute on the right hand side. And only on the left hand side prime attribute must be there. This is also false. And in this example, this is a non-trivial function dependency, and on the right hand side also we can have prime attribute. So option C is false. Option D, non-trivial functional dependencies involving only prime attribute. Yes, everything is allowed except for this. Non-super P key cannot determine non-prime attribute. We can have a non-trivial functional dependencies involving only prime attribute. Example is this only. It is non-trivial function dependencies. A, B, and C all are prime attributes. So D is also true. So the answer is option A, B, and D. So answer is option E. This question belongs to data structure subject and was asked in GATE 1990, and the topic name is binary tree. So the question states, choose the correct alternatives. More than one may be correct. The number of rooted binary trees with n nodes is equal to number of ways of multiplying n plus 1 matrices, equal to number of ways of arranging n out of 2n distinct elements, equal to 2n cn into 1 upon n plus 1 equal to n factorial and equal to both a plus c. So for this question there are some standard things related to the nth Catalan number. So actually this term 2n cn upon n plus 1, it's called, just a second, so this term 2n cn upon n plus 1 is called nth Catalan number. So there are some standard things, just remember them. So number of BSTs. If it is asking number of BST with n vertices, okay, or if it is asking number of unlabeled nodes binary tree, or if it is asking number of structurally different binary tree, then all these three have same answer. So number of ways, so number of these equals to nth Catalan number, which is 2n cn upon n plus 1, and it can also be written as, we can write ACB also can also be written as AB, so we can also write it as 2n cn upon n plus 1. Now there are some more things. The number of binary trees possible. If it is asking number of binary trees or number of labeled nodes binary tree, then both of them are equal to 2n cn upon n plus 1, nth Catalan number into n factorial. This term is extra. And one more thing, yeah, and the number of ways to multiply n plus 1 matrix, either this or to perform n multiplications. So all these four are equals to nth Catalan number, and these two are equal to nth Catalan number into n factorial. So now let us see the options. equal to number of ways of multiplying n plus 1 matrices. Yes, it is equal to nth Catalan number. So what is the answer of this? Its answer is nth Catalan number. Okay, equal to number of ways of arranging n out of 2 n distinct elements. So first we will select the n items and then we will arrange them into n factorial. And what is this? This is the nth Catalan number, and this is just n factorial. So which all are equal? We can see this option A as well as option C, both are equal to nth Catalan number. So just remember these two things, the nth Catalan number and nth Catalan number into n factorial. So the answer is option E, both A and C. This question belongs to data structure subject and was asked in GATE 1990. It basically belongs to binary trees topic. So the question states the total external path length EPL of a binary tree with n external node. Here n is the number of external nodes. It is defined as EPL equals to sigma, which means summation of over all the nodes W and IW, where IW is the path length of the external node W. Then it is less than equal to n square always, greater than equal to n log n always, equal to n square always, order of 1 for some special cases. Let me explain you with an example. So suppose we have a tree like this. Then what is an external node and what is an internal node? It has n external nodes. So external node means leaf node. Leaf node is a 0 degree node, which means it has no child. No child. No child. So which all nodes are no child? This node, and this node. All are 0 degree nodes, which means all are leaf nodes, which means all are external nodes. So we have n external nodes. So what's the value of n here? N has the value 3. And what is the non-leaf nodes? Non-leaf nodes. What are the non-leaf nodes? Non-leaf nodes are this one and this one, 2. And what are total nodes? Total nodes are 3 plus 2, which is 5. Now let us see what is it saying. EPL is defined as external path length, which means it is summation of all the path length of all the external nodes. So path length means number of edges that we need to traverse to go to that node. Suppose if we want to come to this node, then we have to traverse just one edge. So it has path length 1. If we want to come to this node, then we have to travel 2 edges, this one and this one. So it has path length 2. If we want to come to this node, then we have to travel 2 edges, this one and this one. So it has path length 2. So EPL is 5. So we have to tell what will be the value of EPL in the terms of n. N is the number of external nodes. So let me tell you how it can be done. So it says or less than equal to n square always. So to disprove this, let us take an example. Let us suppose we have a skewed tree. Skewed tree means all the child's internal nodes have one child and external and the leaf node has 0 child. Suppose this is a skewed tree. What are the number of nodes? Total nodes. Let us denote it by capital N. It equals to 1, 2, 3, 4, 5 are the total nodes. What are the external nodes? This one is the external node, 1 external node. What are the internal nodes? Let us denote it by IN, internal nodes. It are 1, 2, 3, 4, 4. Okay, now what we can do is that suppose we are adding an extra node over here. So let us first see whether what is the value of this condition, EPL. What is the EPL in this case? So EPL equals to summation of all the external nodes then. So the path length to reach this node is 1, 2, 3, 4. 4. Is it less than equal to n square? What is the value of 1? 1 square 1. 4 is less than equal to 1. It is failing. So here we can easily see that the value it is less than equal to n square is always failing. And here also we can also assume like if we are adding another node like this, then also what is the value of external node? N value is 2. And what is the value of EPL? EPL will be 1, 2, 3, 4 for this and 1, 2, 3, 4. 4 for this, which means EPL will be 8. and 8 is less than equal to n square, 2 square 4, this is also failing. So here we can see that this option is false. Now let us see option B. Option B is saying that EPL is always greater than equal to n log n. So what is the meaning of EPN? EPN means the external nodes length. If we want to, for a given total number of nodes, if we want to minimize, if we want to maximize, or suppose it is lower bound. Suppose if we want to minimize EPL, which means we want to minimize path length, which means IW for all the nodes, which means we should have complete binary tree, or we can say full tree, which means all the levels should be completely filled. So let us take an example. Suppose this is a tree like this. So we have all the full nodes, which means we have a full binary tree, which means all the nodes are completely filled. Now let us see what will be the value of EPL. So here, what is the value of n? N means number of external nodes. It is 1, 2, 3, 4, 5, 6, 7, 8. It is 8. What is the number of internal nodes? 1, 2, 3, 4, 5, 6, 7. 7. It is always equal to, for a full binary tree, it is always equal to 2n minus 1. And it is equal to n. And what are the total nodes? Total node, sorry, this is not equal to 2n minus 1. It is equal to n minus 1. As for n equals to 8, it is equal to 7. And total node equal to n plus n minus 1, which is equal to 2n minus 1. So this has been given to us. Now, for a full binary tree, we know that the height is always equal to log n base 2. Now let us calculate the value of EPL. So what will be the EPL for this tree? EPL for this tree would be height log n, but there would be one less. Suppose here the height is 1, 2, 3, 4 height. What is the EPL to reach this node? 1 for this, 1 for this, 1 for this. Which means for one node it is log n, log base 2n minus 1. This is the path length for one node. And for second node it would be same, log n base 2 minus 1 for this one. And it will continue for n nodes. So what will be the EPL for all the nodes? It will be equal to n into log n. Sorry, we have made a mistake over here. It will be capital N. N means the total number of nodes. It would be equal to capital N, and it will be same for all the n nodes. Log capital N. Log base to n capital N. And what is the value of capital N? Capital N value means total number of nodes. Total number of nodes equal to internal node plus external node, which is 2n minus 1. So let us put the value over here, n into log base to 2n minus 1. So we see that the minimum EPL equals to this, which means EPL will be always greater than equal to n into log base to 2n minus 1. Just remember this, n is the total number of external nodes and n are the total number of nodes in the tree. And here we can prove this statement by, let us assume we are adding a skewness to this. Then if we are adding a skewness to this, then all these n minus 1 nodes will have path length equal to log base to 2n minus 1. And this one node will have path length equal to log base to 2n minus 1 plus 1. So it is definitely greater than equal to n log base to 2n minus 1. Thus this is true. Now let us see option C, equal to n square always. This is false, as we have proved that it can be greater than n square also. As when we take the skewed tree, let us take the skewed tree over here. Yeah, like this. So what is the value of n? N is the total number of external nodes, just one external node. What is the value of n? N means total number of nodes, 1, 2, 3, 4. What is the EPL? EPL is just for this node, 1, 2, 3. EPL is just 3. Whether it is it, and what is the value of n square? N square is 1. So EPL is not equal to n square. So this case fails. And option D says it is equal to order of n for some special cases. No, this is also false, as we have proved in statement B that it is at min it can be n log n. So if it is n log n, then n log n is not equal to order of n, as it is just a linear time and it is linear time into logarithmic time. So this is also false. So the answer is option B, greater than equal to n log n always. This question belongs to algorithm subject and the topic name is time complexity. It was asked in GATE 1990. So the question states, choose the correct alternatives. The complexity of comparison based sorting algorithms is order of n log n, order of n square and order of n root n. So what are these comparison based sorting algorithms? So we have two types. We can classify the sorting algorithm in two types: comparison based and non-comparison based. All the algos, standard algos like bubble sort, heap sort, merge sort, quick sort, selection sort, insertion sort, all of them come in the comparison based sorting algorithm. What is the meaning of comparison based? Let us suppose we are sorting these 13, 1, 5. Then at any point we need to compare two items and check whether A is greater than B or not. These are meaning of comparison based sorting algorithm. And what are non-comparison based sorting algorithms? These are like radix sort, count sort, bucket sort. These comes under non-comparison based sorting algorithm. As here we are not directly comparing the entire number, we may be comparing a particular digit of a number like the ones place or tens place, but not the entire number. So they come in non-comparison based sorting algorithms. So the question is asking the complexity of comparison based sorting algorithms is what? So here we can easily see that there is no standard algo that is being given to us. Like we have not asked like the complexity of merge sort or the complexity of heap sort. So any standard algo is not given to us. So we need to go by general cases. We need to go by general case of proofs. So now let us see. Let us see the meaning of this theta notation. So what is this theta notation? There are three types of notations: big O notation, omega notation, theta notation, as well as small o and small omega notation. So what is the difference between these big O, omega and theta notation? Let us suppose we have the complexity n square. So we can write n square as big O of anything greater than or equal to n square. Like we can write it big O of n square, we can write it big O of n cube, we can write it big O of n to the power 4. Anything bigger would come over here, which means n square is less than equal to anything on the right hand side. And what is the meaning of omega? Anything smaller we can write over here, smaller or equal to. Like we can write it is equals to, let me write greater than equal to over here. We can write n square equals to omega of n square, it is equals to omega of n. We can write it to omega of n log n. We can write it omega of 1. Anything smaller we can write on the right hand side. And what is theta notation? Let us suppose anything which is both big O and omega. Let us suppose we can write n square both as omega of big O of n square, as well as we can write it as omega of n square. So n square is equals to theta of n square, which means it has both the upper bound and lower bound both are same. Then we can write it as theta of n square. Now let us see the options. Here we can see that we have been given the theta notation. Now what we know? We know that in the heap sort, and in merge sort. What is the complexity? We know that all the cases is big O of n log n, which means in every case, which means in the worst case also we will get big O of n log n. In the worst case also, the complexity is big O, which means it is less than equal to order of n log n. Now to find theta, we have to also prove that the time complexity is less than equal to, we have proved this order of n log n. So we have to prove it is greater than equal to omega of n log n. Then only we can say it is equal to theta of n log n. If both the cases happens, then we can say t of n equals to theta of n log n. This one, the right hand side, we can easily see from bubble sort as well as heap sort. and we have to prove this one. Now let us see how we can give a proof for this one. So let us suppose we are sorting a list of n items. Then we can have only one output. Then what are the various permutations that can happen? Suppose we are sorting 5, 3 and 2. So what are various permutations of sorted? It can be either 5, 3, 2, 3, 5, 2, 5, 2, 3. It can be 3, 2, 5. It can be 2, 3, 5. It can be 2, 5, 3. So for n items, we can have n factorial permutation. We can have n factorial permutation, but see, only one of these permutation is correct. So which means what we have to do, we have to basically, let me not remove this yarn. So what we have to do, we have to basically, we will be given n items and we need to combine this n factorial permutation to a single permutation. We need to combine this n factorial permutation to a single permutation 2, 3, 5. So let us see what happens. Suppose, let me give you the proof like this. Suppose we have items like 5, 3 and 2. Then what can happen? We can have all the items in which 5 is greater than 3 over here. We can have 5, 3, 2. We can have over 5, 2, 3. We can have over here 2, 5, 3. And all the items in which 5 is less than 3. Here 5 is less than 3. Here 5 is greater than 3. Like 3, 5, 2. And then we can have 3, 2, 5. We can have 2, 3, 5. Here we can see 3 comes before 5. Here 5 comes before 3. So when we are comparing two items, then we are basically, if we compare 5 and 3, we come to know that 3 is less than 5. So we know that this is discarded, which means we every time using one comparison, we are reducing the set by 2. We are dividing the set by 2. If it was n factorial, then after one comparison, it will become n factorial by 2. After two comparison, it will become n factorial by 2 square. Then it will boil down to 1 at the end. And again, now let us suppose we will compare 2 and 5. And we will come to 2 is less than 5. Then we can discard this. So every time we are just dividing it by 2. Then we will compare 2 and 3 and we will get to know that 2 is less than 3. So we will discard this. So what are the steps in going from n factorial to 2? We are dividing each time by 2. So we can see that we will have log n factorial steps. And what we can write log n factorial? We can write log n factorial to be equal to omega of n log n. It's a standard equation that n log n factorial can be written as omega of n log n, which means we have the complexity omega of n log n to find the sorted array. Now let me brief it up. So what I have told you? I have told you the meaning of theta. When we have upper bound as well as lower bound, both equal to same, then we can write it to be theta. Here we cannot use any standard algorithm. Now let us suppose we have n items, then we will have n factorial permutation. Each comparison reduces the size by 2, so n factorial to n factorial by 2, then divide by 2, then divide by 2, till we will get this sorted array. Here what will be the number of steps? Number of steps will be equal to log n factorial. Log n factorial can be written as omega of n log n. Thus we have best case as omega of n log n. And we got order of n log n from bubble sort and heap sort analysis. Not bubble sort, heap sort and merge sort analysis, as they have all cases omega of order of n log n, which means every case less than equal to n log n. Thus if we can write both omega and big O, then we can write time complexity equal to theta of n log n. So answer is option A, theta of n log n. This question belongs to theory of computation subject and was asked in GATE 1990. And the topic name is recursive languages. So the question states, choose the correct alternatives. Recursive languages are a proper superset of context-free languages, always recognizable by push-down automata, also called type 0 languages, recognizable by Turing machines, and option E, both A and D. So for this, let me clear a few terms. What is the meaning of proper superset? Proper superset means like if this is set A and this is set B. So we can say B is proper superset of A. And this means proper superset proper superset, and this means superset of A. This means superset. Superset means it can be proper superset as well as we can have equals. Like we can also write like this. Here we can also write B is proper superset of A, as B can also be equal to A. But we cannot write B is, here we can write B is superset of A, but we cannot write B is proper superset of A, as proper superset means there must be some of the items which belongs to B but do not belongs to A. So this is the meaning of proper superset. Now let me, for answering this question, you just need to know Chomsky theory of computation hierarchy. I will tell you the hierarchy. So it's hierarchy of languages. So it go like this. Let me draw it. Yeah. It goes like this. 3. Okay. So first we have regular language. It is also called type 3 and it is recognized by finite automata. Then we have context free language. It is also called type 2 language and it is recognized by push down automata. Then we have context sensitive language. It is also called type 2 and it is recognized by linear bounded automata. Then we have recursive language, and we have one more set, this is called recursively enumerable language. It is also called type 0 language and it is recognized by Turing machine. Now let us see the options. So the option 1 states that recursive languages, which means these type of languages are a proper superset of context-free languages, which means a proper superset of these languages, which means they must have something that belongs to recursive language but do not belong to context-free language. Yes, this area belongs to recursive but do not belongs to context-free. So yes, option A is true. Now let us see option B. Option B states that always recognizable by push down automata. Recursive languages. No. Push down automata has range only till context free languages. And these languages are recursive but not context free. So they cannot be recognized by push down automata. So answer B is false. Option B is false. Also called type 0 languages. No, this is also false, as recursively enumerable languages are called type 0 language. There can be some language which recursive are also called type 0, but there are some other languages also which are called type 0 language. So option C is also false. Let us see option D, recognizable by Turing machines. Turing machine can recognize recursively enumerable language, and recursive languages have less power than recursively enumerable language, which means Turing machine can also recognize recursive language. The upper part can recognize the lower language, which means Turing machine can recognize recursively enumerable language, recursive language, context sensitive language, context free language, as well as regular language. But let us think of this linear bounded automata. It can recognize context sensitive, context free and regular, but cannot recognize above languages like recursive language and recursively enumerable language. So option D is true. So answer is option E, both A and D are true. This question belongs to theory of computation subject and the topic name is decidability and undecidability. It was asked in GATE 1990. So the question states, Choose the correct alternatives. It is undecidable whether an arbitrary Turing machine halts after 100 steps, a Turing machine prints a specific letter, a Turing machine computes the product of two numbers, none of the above, or both B and C. Now let me tell you it one by one. Let us see option A. Option A says an arbitrary Turing machine halts after 100 steps. We know the halting problem of Turing machine is undecidable. Halting, as we do not know the number of steps after what we need to halt. But here in this Turing machine, we know we have to halt after 100 steps. There can be two interpretations of after 100 steps. After 100 steps means either exactly after 100 steps, or we can have any time after 100 steps, which means here it will halt exactly between 100 and 101. Here it can halt at any place greater than 100. 100, 101, 102, 103. But here, as it is a standard question, we will assume exactly after 100 steps. It's basically an English question, so here we will assume exactly after 100 steps. This one is undecidable, but this one is decidable. See, the halting problem is undecidable. But if we are given the number of steps, then if we assume exactly after that 100 steps, then it is decidable. And if we assume any time after 100 steps, then it is undecidable. How this one is decidable? As we can run the Turing machine for 100 steps, and then at the next step we can check whether it halted or not. Thus, this is a decidable. It is decidable. Now, let us see option B. What option B says? Option B says that a Turing machine prints a specific letter. See, for option B, we can design a Turing machine. We can design a Turing machine to print. Let us suppose we can design a Turing machine to print A. This is a decidable thing. But if we are given a Turing machine and we are asked whether it prints B or not, whether it prints, let us suppose, A or not, then this question is undecidable, as Turing machine may fall in infinite loop and we won't come to know whether it will print a particular letter or not. Designing a Turing machine, we can design the Turing machine, but given a Turing machine, this Turing machine is given to us. Finding whether it prints a specific letter or not, this is undecidable problem. So option B is undecidable. Let us see option C. Option C is also exactly similar to option B. See, a Turing machine computes the product of two numbers. So the problem of designing a Turing machine to compute A into B, it is decidable. We can do this very easily, as Turing machine has power equivalent to a modern computer only. Now, whether given a Turing machine, but the question states given a Turing machine, whether it computes A into B or not. It is asking this. A Turing machine computes the product of two numbers. It is asking, finding whether a given Turing machine computes the product of two numbers or not. So this problem is undecidable. It is undecidable, as it may fall in infinite loop. Thus, option C is undecidable. Option B is also undecidable. Option A is decidable. So we need to tell which is undecidable. So answer is option B and C. So option E is correct. Both B and C are undecidable. This question belongs to theory of computational subject and the topic name is regular languages. It was asked in GATE 1990. So the question states, choose the correct alternatives. Let R1 and R2 be the regular sets defined over the alphabet sigma. Then R1 intersection R2 is not regular, R1 union R2 is regular, sigma star minus R1 is regular, R1 star is not regular, or both B and C. So you need to remember this for this. There is a shortcut like regular languages are closed under, they are closed under union, they are closed under intersection, they are closed under difference, they are closed under complement, they are closed under clean closure, R star, they are closed under reversal, R reverse, they are closed under concatenation, R1 dot R2. Here R1 minus R2, here R1 intersection R2, here R1 union R2. So what is the meaning of this? The meaning of this is, if R1 and R2 are two regular languages, then R1 union R2 is regular. If R1 and R2 are two regular languages, then R1 minus R2 is regular. If R is regular, then R star is regular. So regular languages are closed under all of these. So if R1 and R2 are regular, then R1 intersection R2, it's regular. And it is saying not regular, so it is false. R1 union R2, yes, it is regular. Sigma star minus R1. So what is sigma star? Sigma star is universal set. So if sigma is, let us suppose, A comma B, then sigma star will have all the possible strings. It will have epsilon, A, B, any combinations, double A, double B, AB, BA, and so on. All the possible strings that you can generate, we will have in sigma star. So sigma star is something like this, and we have R1 something like this. So what is sigma star minus R1? It is R1 complement. So it is equal to R1 complement. So is complementation closed? Yes. So this is also closed. So, and it is saying regular. So it is true. R star clean closure. Is it closed? Yes. But it is saying not closed, non-regular. So this is false. So only option B and C are true. So answer is option both B and C. Option E. This question belongs to engineering mathematics and was asked in GATE 1990, and the topic name is combinatorics. So the question states, choose the correct alternatives. The number of ways in which 5 A's, 5 B's and 5 C's can be arranged in a row is 15 factorial divided by 5 factorial whole to the power 3, 15 factorial, 15 divided by 5, 15 factorial into 5 factorial into 3 factorial. So it's a standard question. Let me tell you the standard formula for this so that you can answer all these type of questions. Let us suppose we are given n items. So number of ways to arrange n items in a row is n factorial. We can select it n factorial ways we can arrange n items. Now let us suppose these n items are divided into three groups, n1, n2 and n3. We have n1 items of suppose type A, n2 items of type B and n3 items of type C. So what are the number of ways to arrange them? So the number of ways to arrange them is n1 plus n2 plus n3 factorial divided by n1 factorial, n2 factorial, n3 factorial. Or we can also write it as n factorial divided by n1 factorial, n2 factorial, n3 factorial. Why this happened was that suppose here what happened is that suppose we have an instance of n1, let us write it as A, then we had another A, let us suppose then we had a B, then we had a C. And now let us suppose we interchange these two, then also it will remain the same. So if we would have given the answer to be n factorial, which means we are considering both these instances to be different, but both of them are same, as we have n1 items of type A. So we have to consider both of them to be 1. So to do that, we have to divide it by n1 factorial. And to make sure that n2 items of type B are considered to be same, we divide it by n2 factorial, and same for n3 factorial for n3 items of type C. Now we have 5 A's, 5 B's and 5 C's. So what are the number of A's? 5 plus 5 plus 5 factorial divided by 5 factorial, 5 factorial, 5 factorial. So it is equal to 15 factorial divided by 5 factorial whole to the power 3. So answer is option A. As all these items are same, we have all 5 items to be same of type A, same to be type of B, same to be type of C. So answer is option A. This question belongs to the subject Engineering Mathematics, and the topic name is Propositional Logic. It was asked in GATE 1990. So the question states, choose the correct statements. Indicate which of the following are true. Which of the following well-formed formula are valid? First one is P implies Q and Q implies R implies P implies R. The second one is P implies Q implies negation of P implies negation of Q. Third one is P and negation of P or negation of Q implies Q. Fourth one is P implies R or Q implies R implies P or Q implies R. So what is the meaning of a formula being valid? A formula being valid means it is a tautology. What is the meaning of tautology? Tautology means always true for all values of inputs. So what are the input? Input can be P, Q and R. So first of all, let me tell you what is the meaning of P implies Q. First, let me tell you the truth table of P implies Q. Let me tell you generic one, A implies B. If we have A implies B, then it is equivalent to negation of A or B. So its truth table would be like the values of A, B, then the values of A implies B. Then we can have 0, 0, 0, 1, 1, 0 and 1, 1. So if you put this value 0 over here, then negation of 0 will be 1, 1 or 0, or let us take in the form of true false. It would be more easier for you to understand. Let us take true true, true false, false true, false false. Okay, so now see. What is the value of negation of true? It's false. False or true? It's always true. Negation of true false, false or false? It's false. Negation of false true, true or true? It's true. Negation of false true, true or false? It's true. So it's false only when A is true and B is false. Now let us draw the table for this option A. So first of all we have P, then Q, then R. Then we have P implies Q. Then we have Q implies R. Then we have P implies R. Then we have P implies Q and Q implies R. Then we have our final result, which is P implies Q and Q implies R implies P implies R. Now let us fill the table. So it can have the values true, 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 false, false, true, false, false. And this can be true. Then for the false, it will have value true, 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 false, false, true, false, false. Then false. So the value of P implies Q is false only when the first one is true and second one is false. So first one is true and second one is false. So here it will be false. First one is true, second one is false. So here it will be false. And rest all, it will be true. This one would be true, 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 true. So it's better to first fill up the false and then put rest of them to be true. So here it will be false in true false case. Then again in another true false case, and rest all will be true. So let us put true all over here. Then we have P implies R. So P implies are, first of all, let us fill false in true false case. This is true, this is false, so it will come out to be false, and rest all will be true. Now this and this, so it will be false if it will be true if both are true. So true and true, true, true and false, false, false and true, false, false and true, false, true and true, true, true and false, false, true and true, true, true and true, true. Then we have this implies this. So it will be false only when first one is true, second one is false. So let us see if we have a true false or not. No, we do not have any true false. So all will be true. Now see, here all the values are true. So it is a tautology. It is a tautology, thus it is valid, well-formed formula. Okay, so the first one is a tautology. Now let us draw it for the second one. So what is the second one? Second one states that P implies Q implies negation of P implies negation of Q. So we don't have R over here. Okay. We have P implies Q, which means P implies Q. Then we have negation of P and negation of Q, which means negation of P, negation of Q. Then we have negation of P implies negation of Q. Then we have P implies Q implies negation of P implies negation of Q. Now let us fill those values. So it can have value true true, true false, false true, or false false. So what is P implies Q? P implies Q table is this: true, false, true, true. What is negation of P? It's false, false, true, true. What is negation of Q? It's false, true, negation of true, false, negation of false, true. What is negation of P implies negation of Q? False implies false. It's false, false, sorry. It is false only for the value true, false. First one true, second one false. Here it will be false, rest all will be true. Now what is this one implies this one? It will be false only when the first one is true, second one is false. So true true it's true, false true it's true, true false. Here see true false it's false, true true it's true. So here we got a false, so it's not a tautology, not a tautology. Thus it is invalid, well formed formula. Thus first one was valid, second one is invalid. Now let us see option C. Here only you can stop the question as it is not a multiple select question. We just have one option, so we have formed a valid well-formed formula which is option A, but still I am explaining you all the options so that it becomes easier for you to do other questions. Okay, now we have third one, P, Q, then we have negation of P, then we have negation of Q, then we have negation of P or negation of Q, then we have negation of P or negation of Q implies Q. So now let us fill this up. So for P, it can have values true, 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 false, false, true, false, false. Negation of P means false, false, true, true. Negation of Q means false, true, false, true. Negation of P or negation of Q means false, false, it's false, false, true, it's true, true or false, it's true, true or true, it's true. Then we have this one implies Q, which means this implies Q. So it is false only for true, false. Let us see true, false. Yeah, here it is true, false. This is true, this one is false. And here also we have the true, false. So it's false, rest all are true. So as we have false, so it's not a tautology. and not a well-formed formula. So this is also invalid. Now let us see the option D. So option D states it has PQ followed by R. So we will write PQ and R, then we have P implies R, then we have Q implies R, then we have P or Q, then we have P or Q implies R, then we have P implies R, we have PQR, we have P implies R, we have Q implies R, we have P or Q implies P or Q, we have P or Q implies R, then we have this or this. Let us rename this as A and this as B, then we have A or B, then we have A or B, and then we have A or B implies, let us rename this as C. Then we have A or B implies C. Now let us fill it up. True, 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 false, false, true, false, false. Now we have again true, 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 false, false, true, false, false. For the values of P, true, 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 false, 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 false. Now let us see P implies R. It is false only for true, false. So here it will be false, true, false. Here it will be false. The rest all will be true. Now let us see Q implies R. False for only true and false. False over here. Rest all are true. Let us see P or Q. So true or true, true, true or true, true, true or false, true, true or false, true, false or true, true, false or true, true, false or false is false, false or false is false. P or Q implies R. So this one implies this. So let us see true, false. So it is false. This implies this. So let us see true, false, false, true, false, false, true, 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 false, 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 false. Rest all are true. Then we have A or B. So this is A, this is B. So it is false only when both are false. When both are false. Rest all are true. Now we have A or B implies C. So it is false when we have true, false. So here we have true, false, which means it is false. Here also we have false. Rest all are true. So as we have false, so it is not a tautology and it is not a well-formed formula. So it is also false. So answer is option A. When you found the first well-formed formula to be valid, you can stop there only. So answer is option A. This question belongs to engineering mathematics and was asked in GATE 1990, and the topic name is graph theory. So it states, choose the correct alternatives. A graph is planar if and only if it does not contain a subgraph homomorphic to K5 and K33. It does not contain a subgraph isomorphic to K5 and K33. It does not contain a subgraph isomorphic to K5 or K33. It does not contain a subgraph homomorphic to K5 or K33. So first let me tell you what is a planar graph. So we can say a graph G is planar. G is planar if and only if, or we can say biconditional. If and only if it can be represented on a plane, and there is a condition such that its edges meet only at endpoints. So what's the meaning of this? Let us suppose we have a graph like this. So here edges are meeting at the endpoints and it is planar graph. Here the edges are only meeting at the endpoints. Here, you may think that the edges are not fitting at the endpoints, but you can rewrite this edge as this. This is also a planar graph. But let us take another example of this graph. So here, now it is planar, now also it's planar, now also it's planar, now also it's planar, but now it becomes a non-planar graph. As we cannot represent it on a plane, here these edges are intersecting over here. Here there is an intersection point, and we can't remove this intersection. As if we come through this direction, then here it's an intersection, and if we come through this direction, then here it is an intersection. Thus this one is a non-planar graph. It's non-planar and it's planar. Now there is a theorem related to planarity of graphs. It's called Kuratowski theorem. Kuratowski. Let me write it more clearly. It is Kuratowski, Kuratowski's theorem. So it states a graph is planar. A graph is planar if and only if, or we can say biconditional, it does not contain a subgraph homeomorphic to K5 or K33. So it's a direct statement of Kuratowski theorem. Or if we apply negation on both the sides, then we can also say that a graph is non-planar if it contains a subgraph homomorphic to K5 or K33. Both are correct. Now let me tell you what is this K5 and K33. So K5 is basically a complete graph with 5 vertices. So this one is a complete graph with 5 vertices, which I have drawn earlier only. A modification to that. This one. It's K5. If we have a subgraph like this in any graph, then it's non-planar. Like if we have a graph like this, let me draw it with another color. Yeah. If we have a graph like this, then it is non-planar graph as it has subgraph as K5. Then what is K33? K33 is complete bipartite graph on which left side has 3 vertices and right side has 3 vertices. So it looks like this. This is complete bipartite graph with 3 and 3 vertices, which means K33. So if any graph has this as subgraph, then it's non-planar, which means this is non-planar. Every graph, any edge or vertex that you add to this will result in a non-planar graph. Now also it's non-planar, now also it's non-planar because it has K33 as subgraph. So the answer is option D due to direct Kuratowski's theorem. This question belongs to digital logic design subject and was asked in GATE 1990. So it's basically a question related to combinational and sequential circuits. So it is asking state whether the following statements are true or false with reason. RAM is a combinational circuit and PLA is a sequential circuit. Now let us see what is a RAM and a PLA. So here are the diagrams for a RAM as well as a PLA. So let me explain you this. So basically RAM, here the input is the memory location selector. This is the memory location selector. This will have as an input to a RAM chip. And another byte which is read comma write bar byte, which can be input for a write operation or output for a read operation. And output is either a success indicator, which tells that we have been successful in writing the operation at the given location, or the byte at the selected location for read operation. Or we can have this data bus which will read the data from the given address bus. Here it does not depend on the past input. RAM is not depending on the past inputs. Like what are the past chip select lines and past address bars? It depends only the present inputs or not on the past write operations at the selected byte. Thus, it is a sequential logical circuit. So option E is false. Now let us see what is a PLA. So basically PLA is a combinational circuit only. It is an alternative to the ROM and PAL. So what is PLA? PLA full form is it's programmable logic device. It has a programmable AND array and a programmable OR array. It has an AND plane and an OR plane. The PLA with n inputs. If we have n inputs, then it will have less than 2 to the power n gates, AND gates. Otherwise, we won't have any advantage over this ROM. A PLA needs to have enough AND gates in order to decode as many unique terms as there are in the functions that it is going to implement. Thus, it is a combinational circuit. It's basically a direct question only. RAM is a sequential circuit and PLA is a combinational circuit. So the option is false. This question belongs to computer organization subject and was asked in grade 1990, and the topic name is modes of transfer. So the question states, state whether the following statements are true or false with reason. The data transfer between memory and I/O devices using programmed I/O is faster than interrupt-driven I/O. We have to tell whether this statement is true or it is false. So suppose we have our CPU and we have an I/O device. So what can be our I/O device? Our I/O device can be a printer, an I/O device can be a keyboard, an I/O device can be a mouse, and etc. So this I/O device wants to communicate with the CPU. It wants to either read some data from the memory or it wants to write some data or give some instruction to the CPU. So programmed I/O and interrupt driven I/O are two modes through which we can communicate. So what happens in programmed I/O is that suppose we have CPU. So we have a program written over here, and based on this program, CPU will give its time, the processing time to the I/O device, which means the I/O can perform an operation. It will allow the I/O to perform the operation. Now, as we know, CPU is faster. The speed of CPU is very fast, and I/O device speed is very slow. So by the time I/O device will complete the operation, in this case, CPU will just wait and check whether it's ready or not, whether it's done. I/O device will keep performing the operation and it will ask whether it's done or not. And by the time it's not done, I/O device is not done the transfer, CPU will keep on waiting. So as CPU is waiting, so it is basically slow, as the CPU is basically waiting and not able to perform other tasks, so it is slow. And what happens in interrupt driven IO is that interrupt is basically a hardware signal. Suppose we have an IO device like keyboard. So whenever we type, what is happening is that we are giving an interrupt signal to the CPU. We are sending an INTR, which means interrupt signal to the CPU. And then CPU will execute the I will give the basically commands to the IO device based on this interrupt signal, and we basically have a code written over here which tells interrupt service routine, which tells what tasks need to be performed. And for all the time for which the CPU hasn't received any interrupt request, it will keep processing. So its CPU will be busy doing productive work. It will be busy doing productive work, as it will allow the IO device to, as IO device will keep performing its task, CPU will keep performing its task, and when IO device is done, it will just send an interrupt signal. So interrupt based IO is faster. So programmed IO is slow and interrupt IO is faster. And the question is saying the data transfer between memory and IO devices using programmed IO is faster. It is saying programmed IO is faster. It is false, as programmed IO is slower. So answer is option B, false. This question belongs to computer organization subject and was asked in GATE 1990. And the topic name is instruction execution. So the question states, state whether the following statements are true or false with reason. The flags affected when conditional call or jump instructions are executed. It's true or false whether flags are affected during conditional call or jump or not. So what is a flag? Flag is, suppose we have a CPU or a processor. Then it basically have flags. Flag is basically 1-bit memory on CPU. 1 bit means it can either have a 0 value, it can have a 1 value. If it has a 0 value, then it is called reset. Flag is reset. And if it has 1 value, then it is called flag is set. Now there can be various types of flags like 0 flag, carry flag, parity flag, sign flag, overflow flag. So they have values 0 or 1. Either they have a value 0 or a 1. So 0 flag has a value 0 means the operation that we are performing has answer as 0. Carry flag means that there was a carry present. There can be two types of parity. Parity can be even parity or odd parity. If we have even parity and the number of set bits are even, then it has a value 1. And if we have even parity and the number of set bits are odd, then it has value 0. Sign flag checks whether the MSB is positive or negative, like the number is positive or negative is indicated by sign flag. Overflow flag tells whether when we are performing calculation whether we got an overflow or not. Now, suppose we are running a program. Now, during program, if we want to jump from this place to another place, if we want to jump from place P1 to place P2 in the code on a particular condition, then it is basically represented by instructions like JZ. JZ means jump on 0. J and Z. Jump on if the value of 0 flag is reset. Jump on carry. Jump if the value of carry flag is set. Jump on not carry. Jump if the value of carry flag is not set. Jump on parity, jump on non-parity. We have instructions like this. They will be written over here like JZ. Now if we have JZ, we will go to the CPU and we will check the 0 flag, whether it's set or reset. If it is reset, we will do nothing. If it is set, we will go to place P2. Thus, we are only checking the values of these flags. We are not updating them. We are only reading the values. And it is saying flags are affected. Affected means they are changed. But we are only reading. Thus, this option is false as we are only reading, not changing the values of the flags. This question belongs to computer organization subject and was asked in GATE 1990. And the topic name is cache. So the question states, state which of the following statements are true or false with reason. Transferring data in blocks from main memory to cache memory enables an interleaved memory unit to operate unit at its maximum speed. So let me tell you what happens. Suppose we have main memory. So main memory we know, or RAM, has low speed. So we divide main memory into blocks. And then we have cache memory. Cache memory has higher speed. And we divide it into words. And one block size equals to one word size. So a block is moved to a word of cache. Okay. And then CPU directly accesses from the cache. If cache miss, then we bring the block to the cache and then we access it. So what is this interleaved organization? We can have two things. Suppose we can have RAM chips in a single memory unit. We can have in a single memory unit. We can have only one memory unit. Then addresses will be sequential. Suppose this is 32 address, 33 address, 34 address, 35 address, and due to locality of reference, CPU will access them in the sequence only. So what happens? Suppose CPU send a read request on 32, read and write request. Then it sends on 33. But there is some time difference between read and write operations of each memory chip. So here after 32 reading, it will take some delay and then we will read from 33. Then after some delay, we will read from 34. So this is slow organization. And what is a faster one? Let me tell you. So what happens is that now we are having RAM chips. And RAM chips are combined, DRAM chips are combined to form RAM modules. Suppose module 1, module 2, module 3. and then we have CPU. And the addresses are random, like 32 over here, 33 over here, 34, then 35, then 36, then 37. And due to locality of reference, we will call the addresses sequentially. So suppose when we call 32, then we go to 32, get the block, read write, and there is delay only in this memory chip. And when we call 33, then we can go to the second memory chip without any delay. Then we can go to the third memory chip without any delay. And then we can come back again to the memory chip 1. So it goes alternating between the memory chips. Thus, this is faster as there is no delay. So answer is true. This given statement is true. This question belongs to operating system subject and the topic name is linker. It was asked in GATE 1990. So the question states, state whether the following statements are true or false with reason. The link, load and go loading scheme require less storage space than link and go loading scheme. So suppose when we have a program, suppose we have example1.c program, then it goes through various steps, like we have compilation step through compiler, which converts this high level language to assembly level language. Then we have assembler. So what assembler does is that it converts this assembly level language into low level language. Then we have linker. So linker links what are the various files for which reference is not present. Like for the functions which are not present, like we may include some library, and then we may use some functions of the library. So linker does the linking of that functions. Linker. Then we have loader. Loader basically loads a program to main memory. Loads to main memory address. So now we get the low level language. Now there are two types of loading scheme: link, load and go loading scheme. In this loading scheme, the linker or the link editor need not be with the main, like we have program in a RAM, we have program over here. In this loading scheme, the linker or link editor need not be present with the program. But in this link and go loading scheme, the linker or the link editor, suppose we have a program over here, then the linker or link editor also need to be present along with the program in the RAM. So the second one will occupy more space. So the first one, the link, load and go loading scheme requires less storage space. So the answer is true, option A.